The mission of the Weinberg Institute for Theoretical Physics is to research groundbreaking ideas in astrophysics, cosmology, gravitational physics, and particle theory. To do that, we have 3 centers within the Institute. There's the Cosmology Center, which we call TCAP. We have the Center for Gravitational Physics, and we have the Theory Center. These ideas all talk to each other. People don't just work in one area in a silo. That's what's so wonderful about the Institute is the cross-fertilization of ideas between the people in these 3 different fields.
Dark matter is a very important component of our universe that we understand very little about. So the part of my research program that I'm most interested in is trying to understand what the fundamental nature of dark matter is at its most fundamental level and understand how those properties go and impact the largest observations that we have of our universe.
A fantastic part about being at the Weinberg Institute and at UT Austin is they have formally joined the Simons Observatory as an institutional member, and that gives us access to data and capabilities of the Simons Observatory. The Simons Observatory itself is effectively the most ambitious cosmic microwave background experiment to date. It is a series of telescopes down in the Chile's Atacama Desert, about 17,000 feet down there. We started in 2016. It got first light in 2023. So we're about a year and a half after getting data, and we're just starting to see the wealth of data that it can provide and start to see what we're actually capable of doing with it. And so it's a really exciting time to be part of that project as this data is coming in and having the resources here, both in my colleagues as well as the junior members, the postdocs and graduate students that are able to take advantage of this rich data set as it comes in.
My research area is quantum gravity, more specifically something called holography. In holography, the idea is that we can describe a theory that is quantum by another theory encodes the same degrees of freedom in a completely gravitational quantum gravity theory. So for example, one thing that I am interested in is how do we describe the interior of black holes? Can the interior of black holes be mapped to a completely quantum system? How can we describe the singularity inside the black hole using this holographic duality? Those are like some of the questions that I am interested in right now.
We study the connections between phenomena occurring at the largest observable distance scales. I mean, the size of the entire visible universe, which is the purview of cosmology, with phenomena occurring at the shortest distance scales where quantum gravity and string theory dominate. Finding the connections between those two is kind of what we're all about.
I study cosmologies and nuclear astrophysics using black hole and neutron star mergers detected in gravitational waves. To measure the universe expansion rate, we need to know an astrophysical object at different distances, how fast they move away from us due to the universe expansion. So we need 2 things. We need the distance, so how far they are, and how fast they move away from us, which is known as a concept of redshift. Studying their signals, we are able to determine one of the key components, the distance from the gravitational wave signals.
The gravitational wave signals we've detected using the LIGO and Virgo instruments have told us a huge amount. It's really completely transformed our understanding in some ways, not necessarily by revealing unexpected new physics, but by revealing unexpected new things out in the universe. So they've shown us how binary black holes actually do collide and merge and have verified our understanding in the theory of that. But they're also beginning to teach us a huge amount about other things. These waves are coming from some of the most extreme systems in the universe, and so they really allow us to probe fundamental physics and probe matter at the extremes and many other applications.
So I really do love working here at the Weinberg Institute. I think it's unique because of the depth of expertise and also the breadth. We really benefit from being in an environment where you have all these experts looking at a similar problem but from different viewpoints and bring different tools to bear. What could be better?